Hello, welcome to your first lesson in geometry. Today we're covering Chapter 1, Section 2. We skipped over Section 1, it's about isometric drawings. We may cover a little bit of this on the first day in class, but it's not in our standard, so we're not going to spend a whole day on this section. All right, so this is points, lines, and planes, three basic building blocks of the language of geometry. So we'll talk about those today. First, we have a warm-up though. If you haven't tried the warm-up yet, you need to do it yourself. It gives you a place to practice problems on stuff that we've learned already, and then come back and check it over. It's kind of like taking a mini quiz every day in the notes, and it only helps you if you do it yourself first. All right, so since we haven't had any geometry lessons yet, this is our first thing, so it'll be a little algebra stuff. So simplify each expression. So we're using order of operations, and if we run into the symbol pi, we're going to put 3.14 in its spot. So our first problem is 3 to the second power, or 3 squared. 3 squared is 9. Our second problem is 4 to the second power, which is 4 times 4 for 16. Our third problem, we have multiply and we have adding, so two parts of the order of operations. You do the multiply first, and then the adding. And please show the extra step of work. Don't do the whole thing in your head. Okay. And number 4, we have pi times 5 squared, which is 25. And then we're rounding here, so we'll do the squiggly equals. And 3.14 times 25 is 78.5. Okay. So the squiggly equals, remember, is our approximate sign. All right, number 5, 5 squared is 25. Remember, the square root bar, our square root house, acts like parentheses or grouping symbol in the order of operations. 12 squared is 144. We can add them together inside now, so this will make 169. And the square root of 169 is exactly equal to 13. All right, number 6, we have absolute value bars here. They act like a grouping symbol also, so we have to work out the inside first. 3 minus 8 is -5. And then the absolute value of -5 is +5. Don't be tempted to do the absolute value of 3 and the absolute value of 8 and then subtract them. Remember, we have to do the subtraction first. All right, so then we have a little practice on solving equations. So here we're going to move the 7 over first. So 13 minus 7 is 6. And then divide by 2 for 3. And the second one, we'll get all the x's on the same side. So I'll subtract 2x from both sides, which will make 3x minus 12 is 6. And then I'll add 12 to both sides to get 18 and divide by 3 for 6. Okay, and then in our last one, I'll distribute the 2 first, trying to simplify the left side of this equation. Continue simplifying the left side by putting the like terms together. 6 minus 1 is 5. I'll get all the x's on the same side. I'm going to move everything to the right side because the right side has only x's. So I'll subtract 2x from both sides to get 5x. And then I'll divide by 5 to both sides to get 1. All right, this concludes our first warm-up. Let's see what's on the second page. Okay, if you look in your math book, you're going to find the following definition. Geometry is a mathematical system built on accepted facts, basic terms, and definitions. Okay, so this accepted facts is important here. We're going to have to accept a couple facts before we can start building the language of geometry. And then we use those accepted facts and basic terms to build definitions. Okay, so we have to accept these facts first. Okay. You can also think of geometry as a language of math that covers 2- and 3-dimensional objects. Okay, we learn the properties of them and how they interact together. So in geometry, some words such as a point, a line, and a plane are undefined. These are our basic terms or basic facts. We all have to agree what they mean because there's no way to write a definition. Okay, undefined terms are basic ideas that you can use to build the definitions of all the other figures in geometry. So we all agree on what these mean, and then we can write a whole language of math. Although you cannot define these terms, you do need to have a general description of their meaning. So here's a general description of what a point is. A point indicates a location and it has no size. Okay, so it's just a place in space. We all agree what it means, but you can't really define it well. If you can't see it, you can't touch it. Okay, all right, you can represent a point by a dot. Okay, remember this is just a representation. This dot here has width and it has length. Okay, it's this little circle I'm drawing on the board, and you can name it with a capital letter such as A. So this is how we look at points in a diagram. We call it point A, like this, or if we want to write it in words, we say point A. All right. Now, a line is represented by a straight path that extends in two opposite directions without end, and it has no thickness. So we took something that had no size at all, we put a whole bunch of them in order together in a line, and notice I'm using the word line in the definition of line. This is why we can't define it, okay? But we all know what it means. So we put them all in a row, and then suddenly we have a line. So now we have one-dimensional space, something that goes left and right only, okay? Has no width and no depth. You can name a line by any 2 points on the line, such as AB. Okay, remember there's infinite many numbers of points on there. I just put 2 dots and called them A and B. And we would write it like this. AB with a little line with arrows above it. Without arrows means something else. We read that out loud as line AB. We could also define it as line BA. It doesn't make a difference. And there's one other way to define it. You can use a little lowercase cursive letter out by the arrow. In this case, they used an L. So we could call this line L. All right. And then we have one last building block, okay? A plane. A plane is represented by a flat surface that extends without end and has no thickness. So here is my plane. Kind of think of it as a piece of paper that would be infinitesimally thick. Okay, so you couldn't actually write on it because you wouldn't make anything that way, the up and down part. But left and right is fine. You can also think of it as an infinite number of points that go on in 2 directions, up and down and left and right, or a line that's been extended over and over next to each other. So a whole bunch of parallel lines next to each other. Okay. All right, you can name a plane by a capital letter out in the corner. You're supposed to use a cursive capital letter, so that's plane P. Notice there's no dot by that P there. Or you can name it by 3 points in the line that 3 points in the plane that are not on the same line. Figure out why they can't be on the same line in a minute. So kind of think of it as these 3 points have to make kind of a triangle, and they define where the plane is. So the plane is a flat surface like a piece of paper. A line is like a pencil, and a point is like the tip of the pencil. Okay. So why do you need to write a description of a point before we write a description of a line? Well, we use the description of a point in the description of the line. So we use points to help us define what the line is. All right? Now we're not really defining it, but help us explain what the line looks like. Why do you need at least 2 points to name a line? Why not just call it line A? So for instance, here's line A. Okay. Looks fine on paper. When I say it out loud, oh, that's line A, I can see it. But guess what? There's other things that could be line A. We just didn't draw them in. There's another line A. Here's another line A. Here's another line A. How many line A's are there if I only use 1 point? Well, that's infinite. We can keep spinning it just a little bit more. Okay, so you need 2 points to name a line, not just 1. Otherwise, we have infinite number of lines go through each point. Okay, so if I tried to define it by just 1 point, then I don't know really what I'm talking about. Yeah, we can draw a picture of 1 line there, but somebody else could come along and draw 5 other pictures that could go through their point. Okay, so why do you need at least 3 points to name a plane? It's going to be very similar. So here's 2 points. Okay, I'm going to go ahead and draw a plane that goes through those 2 points. All right, that lays right on the side of it. Think of 2 points on there. And then here's another one that goes through these 2 points. Let's see if I can do this. And I think I'd better try that picture again. So let's do this one more time. Why do you need at least 3 points to name a plane? So here's 2 points. I'm going to draw my plane so that the points are kind of on the edge, even though they're not. Okay, the plane goes on forever. And then I'm going to draw another plane. Okay. There's another one there. And I'm going to draw another one like this. Okay, so there are infinite number of ways to draw planes that go through those 2 points, because all 3 of these planes share the line that goes through them, like that. Okay, so the more we add, the harder it is to see that picture. But kind of think about taking 3 or 4 pieces of paper and making them all intersect at the edge. And you can see how many planes would go through those 2 points that are on the edge. So this is the same problem as above, infinite number of planes pass through every 2 points. Every 2 points. Okay. All right, points that lie on the same line are called collinear points, and points that lie in the same plane are called coplanar points. Not because they like to complain, but because they're on the same plane. All right, so all the points of the line are coplanar. So if you have a line, all of those points are coplanar, but there are infinite number of planes that go through them. Okay. So let's do a couple naming here. What are 2 other ways to name line AB? All right, so line AB is supposed to be coming from above the plane, and then it cuts down through it and then goes on afterwards. So that's the dotted part that's underneath the plane. Okay, so a couple ways to name line AB. We could call it line L, because there's a little L out by the AB. We could call it line BA. Now we're only asked for 2, but we could also call this line AF. F is on that same line, or FA. Okay, so there's 4 ways. Okay, what are 2 ways to name plane Q? So we just need to think of 3 points that are on the plane that aren't in the same line. Okay, so we have a couple choices here. We could call this plane, and we could choose E and A, and pair it with C, okay, in any order of those 3 points, by the way, or plane, and then we could choose A and D and pair it with C. You could also do E and D with C, and then my question for you would be, why can't you use EA and D, plane EAD? Okay, and that would go back to our description of a plane, which is we need 3 points that are not collinear. Okay, so what are names of 3 collinear points? Well, I kind of gave that away, so there's 2 choices here. EAD are collinear. Okay, what are the names of 3 collinear points? So points E, A, and D, and I should probably write that with the word points there. And D, or points, let's see, there's another set, B, A, and F. Okay, those are the line that goes straight through the plane. All right, what are the names of 4 coplanar points? 4 points that are on the same plane. So in this case, the only points that are on the same plane are C, E, A, and D. Okay, so points C, E, A, and D are all on the same plane. All right, so line M is that EAD line, the line that holds E, A, and D together, and line L has B, A, and F on it. Notice A is on both of those lines. And then the plane cannot use the 3 collinear points EAD to define it. Okay, and it's plane Q because of the Q down here. All right, let's flip it over. Though the terms point, line, and plane are not defined, remember we could just give descriptions of those, we can use those descriptions to define other terms, okay? So a term description. A segment is a part of a line that consists of 2 endpoints and all points between. Okay, so these are some defined terms. This is how we define a segment. It's part of a line, so not a whole line, just part. And it consists of 2 endpoints and all the points in between. So in this case, in my picture, I have endpoints A and B. That's where the segment ends. And there are infinite number of points between A and B. We just don't try to draw them all in there. Okay? You can name a segment by its 2 endpoints, such as AB. Notice in this case, there are no arrows above the A and B on that line. And you read it as segment AB. Or you could just flip it around just like we did on a line and call it segment BA. All right, so array is part of a line that consists of 1 endpoint and all the points of the line on the other side. So it goes on forever. Okay, so in this case, here's our picture. There's the endpoint, and then all of the other points on that side of the line are included. So I just drew one in there, B, because we need one more to define it. Okay, and then we can add as many as we want after that. Okay, so you can name an array by its endpoint and another point on the array, such as AB. In this case, we can't flip around the order here. Okay, array BA would mean something different. And then if we say it out loud, we say array AB. Okay. Opposite arrays are two arrays that share the same endpoint and form a line. So think of it as like just split the line in half. Okay. So you can name opposite arrays by their shared endpoint and any other point on each side of the array. So this is array CA over here in blue, and this is array CB over here. Okay, so we have three new definitions. We have array, we have a segment, and we have opposite arrays. And these are actual definitions. They just use our undefined terms. So, but we can define things with those undefined terms now. Okay. All right, so what is the name of the segments in the figure at the right? So all the segments here. So we have segment MN, that's one. We have segment NP, that's another. And we have segment, let's see, MP. Okay, so the first one, MN, defines this piece. The second one, NP, defines this piece. And the third one, MP, defines that piece. Okay. Now you could say, oh, well, what about segment NM? Well, it's the same. It didn't say give all the names for each of the segments, just said name all the segments. So there are three segments, so I have three names. Okay. What are the names of the arrays in the figure at the right? So let's see if we can find them all. Okay, so we need an endpoint, and we need one other point on the other side. So here we have this. We could do MN. So that's starting at M and going that way. Okay, so we've got one. All right, we could also do NP. It's going to be a bit shorter. Not really, because they both go on for infinite, but it starts at a different place. Okay, cuts off that little place, that line segment between M and N. Okay, now we have some arrays that go the opposite direction. So we have P and then N or M, it doesn't matter which one. And we have N and then M. Now what about just M? Remember though you need, so I'm asking this question, what about we just say array M and then we start from here and go down? Remember to define array or line segment, we need 2 points, okay? All right, which of the arrays in exercise 15 are opposite arrays? So which ones have the same endpoint but go in opposite directions? And that's gonna be NP and NM, okay? All right, a postulate or an axiom is an accepted statement of fact, okay? Postulates like undefined terms are basic building blocks of geometry. They do not need to be proved. So this kind of uses our definitions for words and terms we've learned, but we don't have to prove this. And we'll learn what kind of things have to be proved later on, and we'll do lots of proofs later on. So this is some basic building blocks. So postulate 1-1, and we're not going to memorize them by 1-1. We're going to memorize them by what they say. Through any 2 points, there's exactly one line. Okay, that makes sense. If I draw 2 points, there's only one way to draw a line that passes through both of them. I can't make my line go like this. Otherwise, it's no longer a line, it's a curve. Okay. Any two distinct lines intersect, they intersect at exactly 1 point. So if I have 2 lines that are separate, they can't be the same line. And if they intersect, they only intersect at 1 point. There's only one way to do that. Okay, this is why these are postulates. We don't have to prove them. It just makes sense. That's the only way you could do it. Okay. Now, notice it says if they intersect. So 2 lines actually don't have to intersect, but we have to think a little more three-dimensional here, and we'll learn about what kind of lines those are later on. Okay. So postulate 1-3. Remember, we're not memorizing them by the postulate names. In 2 distinct planes intersect, they form exactly one line. Okay. So here's 2 planes. Draw one this way. And I'll draw one this way. All right, so we got two planes and they intersect. So some of these parts should be dotted here, but they intersect at this line right there. Okay, so one of these planes is on top of the other, and we'd have to decide which one. Okay. All right, so two planes that intersect, they intersect at only one line. Okay, not all planes are going to intersect it. Think about two pieces of paper hovering above each other. That would be flat on top of each other, so kind of like parallel for planes. Okay. All right, so what does intersect? Intersect means to cross. Okay. All right, flip it over. Our last question, a couple questions. What is the intersection of plane AEH and plane EGH? So AEH is the red one, and GEH is the blue one. And two planes are going to intersect to form a line. That was one of our postulates on the back page here. And the place where they intersect is right there. So what is the name of that? Well, that's line EH. We can't do EH as a segment or array because we need it to go on forever in both directions because those planes go on forever in both directions. Okay. All right, so our last postulate, postulate 1.4. Through any three non-collinear planes, there's exactly one plane. All right, so any three non-collinear points, there's exactly one plane. Which part of the box is represented by plane QRP? So RQP is this one, and this one. So what part of the box is represented by plane RQP? I would say the bottom. Okay. Which part of the box is represented by LKJM? LKJM, well, that's the top. That's this piece right here. And which part of the box is represented by JRN? JRN is the left side of the box. Okay, that's over here. This plane that contains J, R, and M. So that's the left side of the box. All right, so we're not going to memorize these postulates by their numbers. We're going to memorize the names. And what you really want to do is get a little back of your notebook and just start writing them all down. Okay, and then every day you flip through them and see if you can say what they are. Through any three non-collinear points, there's exactly one plane. Okay. All right, down below here, there's a check for understanding. Ooh, lost a D in there, sorry. Work these problems individually, and then you'll have some time next class to discuss them with your table before presenting solutions to them. So there are 8 problems, and this will be kind of like our warm-up next class. Okay, so you're going to present them in class. All right, so work through them, and then come prepared to present your answers to your table, and then your table to present the answers to the class. All right, I'll see you in class next time.